What is normal modes of oscillation? Normal modes of oscillation is very useful in studying crystal structure. We know in traveling wave, the system can oscillate with any arbitrary frequency. The traveling wave can be represented by the equation y is equal to a sine kx minus omega t. K is the wave vector, omega is the angular frequency. So a traveling wave can oscillate with any arbitrary frequency. But in case of a stationary wave, the system can oscillate with a set of natural frequency. For stationary waves or standing waves, the frequency, the oscillation frequency is not arbitrary. You have some set of frequencies for that system. These set of natural frequency are called normal modes of oscillation for that system. So normal modes of oscillation is basically for standing waves or stationary waves. Consider two traveling wave. One is your y1 is equal to a sine kx minus omega t, suppose traveling in this direction, and another traveling wave y2 is equal to a sine kx plus omega t. It is traveling in opposite direction, and they are producing a standing wave as shown to you in this figure. And the system have a length L. Within this length L, they are producing a standing wave. So from superposition principle, the resultant displacement y will be equal to y1 plus y2. So y1 is equal to a sine kx minus omega t, y2 is equal to a sine kx plus omega t. If you use this equation, trigonometric equation, sin a plus b plus sin a minus b is equal to 2 sin a into cos b, then the result of this addition will be equal to 2a sin kx cos omega t. Here 2a sin kx, this is called the resultant amplitude of the two waves. So the resultant amplitude is equal to 2a sin kx. And in standing wave, you see you have points of zero amplitude. This is the point of zero amplitude. These are called nodes, and these are the points of maximum amplitude. This is called antinode. Don't confuse with nodes and modes. Modes are different and nodes are different. Okay, the zero amplitude points are called nodes and maximum amplitude points are called antinodes. Suppose in a system you have nodes at the ends. So what will happen? We know for node the amplitude is 0. So 2a sin kx equal to 0, but that is equal to sin n pi, where n is equal to 0, 1, 2, 3, etc. Since 2a is not equal to 0, sin kx equal to 0. So sin kx is equal to sin n pi. So kx is equal to n pi. And we know wave vector k is equal to twice pi by lambda. So twice pi by lambda into x equal to n pi. So x will be equal to n lambda divided by 2. And we have taken x equal to L. So L will be equal to n lambda by 2. So lambda is equal to 2L divided by n. But we know v equal to n lambda. V is the velocity of the wave. So v is equal to nu lambda. Here we have taken nu, frequency is equal to nu. So v equal to nu lambda. So lambda is equal to v by nu. So if you substitute lambda is equal to v by nu, then v by nu is equal to 2 lambda divided by n. So nu will be equal to nv divided by 2l, where n is equal to 1, 2, 3, etc. So if you put n is equal to 1, then nu is equal to V divided by 2L, putting N is equal to 2, 2V divided by 2L or V by L, putting N is equal to 3, 3V by 2L, this is 2, 3V by 2L, etc. So the system will oscillate with this natural frequency. These are the natural frequency with which the system can oscillate. This system cannot oscillate with any arbitrary frequency. The system will oscillate with these natural frequency. And these natural frequencies are called normal modes. Remember, these natural frequencies are called normal modes if at the endpoints you have nodes. But if in the endpoints you have if antinodes like this, if you have a system where at the endpoints you have antinodes, then nu will be equal to n plus half v divided by 2l. You have to use this equation. So remember, the lowest possible frequency is called fundamental mode. This mode v divided by 2l, this is called the fundamental mode for the system where you have nodes at the endpoints. And the fundamental mode is also called the fast harmonic. Remember, the fundamental mode is also called the fast harmonic. So normal mode is very useful in lattice vibration. In lattice, you have in lattice vibration you have standing waves. Standing waves will be produced, and the frequency of the standing waves, they are fixed, and they are called the normal modes or the natural frequencies of the vibration of the system. So this is very useful in solid state physics.